Yeah, sure. Oh, well, there's always something. Anyway, we talked about the elements that make data pad, basically the hardware that we need to make one data pad. So what are the elements? Anyone? Feel free to read. Yeah, they are there. So we need definitely a program counter to tell us where is our program at. We need the memory to tell us what is stored on that particular address where program counter is pointing to. We need register files to make communication between arithmetic logic unit and memory a little bit faster. And we need instruction register, and that's the new element, and I'll explain in a moment why do we need that. So you saw how a register looks like. Basically, you need a clock to tell him when to read the input and when to load out the output. Basically, you need orchestrator to tell the units when to run. And then you talked about rising and falling edge, right? How you start the clock. So do you know why are we using the rising edge or the falling edge rather than the high or low level? So if we have a clock like this, you can clock it on the rising edge. You can clock it when it's high level, when it's low level, or when it's falling edge. So anyone knows why do we prefer this rising and falling edge over the flat line? Yes? Well, you can do the same thing here. If you wait long enough that you can read this is, let's say, level 1 and this is level 0, you can say, okay, now when it's 1, I'm going to read the level, or when it's 0, I'm going to read the level. The reason for that is that our transistors are not perfect, and this clock doesn't look like this. It looks more like, okay, we had some 0, and it's not constant exact 0. It's a small number, and then it starts rising, and it doesn't rise right away, and then it has a slight oscillations until it settles to 1, and then it starts falling, and again it takes some time to fall, and then settles down to 0. So what happens is it's much easier to recognize when the level starts rising, basically when it's higher than if this was level 0. I can say when it's 0.2, it has obviously risen high enough that there is no doubt is it 0 or something else. And then I can turn on my clock. Here, if I wait for this thing to settle down to 1, it may take a longer time, so I may have actually shorter time to execute my instructions. So that's why we prefer rising over falling edges, because it's just easier to detect. Because you are not supposed to make an error. If you clock something in a wrong time, you will mess up everything, and that's not a good thing. So anyway, that's about it. You saw the memory. Memory has address input, data input, read, write, and the data out. You need address to tell in which line of a memory you're supposed to read or write. If you're writing something in a memory, this unit here, write, will be 1. If you're reading, it will be 0. So it's pretty much one wire, 1 bit. And then you have a data in when you're writing and data out when you're reading. So you talked about how to connect one data path element. Basically, if you want to add 2 numbers, you will have a PC that says, okay, where in a memory I'm supposed to read this instruction. My instruction is add, let's say, Rx, Ry, Rz. So I'm adding Ry and Rz and storing it in Rx. So PC will tell me which address in memory I need to read this instruction. So once when I do that, then my data store, then memory stores in instruction register basically this whole instruction. And in reality, it will be a bunch of zeros and ones. If you remember how we defined this instruction, the first 6 bits were for determining is it addition, multiplication, and so on. Then you have 4 bits for Rx, 4 bits for Ry, 4 bits for Rz, and some extra bits that we are not using. So that will be stored in instruction register. So why do we need instruction register? Can we just, every time when we need extra register, basically read the memory? Theoretically, we could, but it's not very efficient. So we take one extra register called instruction register, store all this information, and then we will see. First, we have to fetch in the instruction. Then we need to decode it to figure out what is the instruction. Then we need to fetch these registers to perform the operation. So we want to have the whole thing in one place where we can access it easily. So then we store this information into basically register file. We fetch Ry, Rz, we put them into AUL, add those two numbers, and store it in Rx. Yes? Instruction register just holds this line of a program in it. And then we will, I'll show you how data path is actually orchestrated. Because right now we are just putting all these units together, but there has to be someone who decides who is reading, who is writing, and so on. So I'll get to that point. This is just to show you all the elements. So now imagine that you want to do subtraction, or you want to do something more complex. Do we have to make all these connections every time for each instruction? Wide guess. Imagine how many wires would you have if we have to do that. Because if you think about it, let's say this D out will have a 32 wires because we have 32 bits to store here. Then you would have a 32 wires going in here. So what do we do? You're free to guess. Okay, I'll tell you what we do. So I will skip this part. Did you talk about how to decide what is the width of the clock? How many instructions you can do within one clock? You talked about that. So that's this slide. Basically, it's telling you that in one clock you will read PC. PC address will get into memory. Memory will store the instruction in instruction register. And then in the next clock, you will read registers, add the numbers, and store again in a register file. And this is just example. So basically, to make things more approachable or easily approachable, we make something like this. These functional units would be, let's say, this is your PC, this is your memory, register file, instruction register, and you connect them all on one bus, on one big wire. Now, how do we communicate? How these functional units communicate? Well, if you want to write something on a bus, you activate this drive. Basically, this functional unit wants to write something on a bus. This drive will become 1. And it's, let's say, 1 bit. And now your 32 bits are on this line. And as you can see, every one of these functional units can read it. So if I activate these 2 units to read, basically letting this latch to be 1, then they can read whatever is on the bus. Now, do you have any questions? Can two of them write at the same time? Why? Well, if you let them write at the same time, and that's probably the answer to this question, what will happen? So if two of them, yes? You can look at that as, let's say this way, if we want to look at a digital signal, if I had a bit from one unit be 1, and then from another unit to be also 1, basically on my bus I will have two ones, which means that my voltage will be 2 volts. And my bus is designed to support, let's say, 1.5 volts, mainly because I'm assuming that I'm transmitting 1 volt or 0 volts. So 1.5 is just for protection if there is some oscillation in a voltage. So if I now put 2 volts on my bus, A, data will be definitely corrupted. B, you will have a possible smoke or fire. If processor doesn't shut down, it will burn. So pretty much all 4 answers are correct, and they will happen in this order. Basically, if that happens for a very short period of time, it may not burn. I mean, there are ways to prevent fire, but it's a really bad idea. Exactly. I'm always giving you a hint, so feel free to answer the question. So what do we do? Let's say we want to do the same instruction as before. So we will have now PC right on one bus, and that information will be read by address unit in the memory. Once when it's read, it can go down on the other bus and be stored in instruction register. In a previous case, we had to wait for PC to write into memory, and then can memory write again on the one bus because everything is connected. Here they're disconnected, so you can do 2 writings in 1 cycle. Now the second cycle will be again to read 2 registers, X, RY, and RZ, and then add them together and write the result in RX. So in this case, we didn't have to use 2 buses. But usually you design one way or the other because it's really hard to change hardware when the processor is done. You may have more buses if you need, but in our course, we will focus only on single bus. Do you have any questions? No? All is clear? Okay. So let's go to finite state machine. Who is familiar with that? Everyone, yay. Okay, so what is a finite state machine? It's basically the way to describe certain logical circuits, how they are connected and who is controlling what. So here we have S1, S2, and S3 as states, and we can go from stay in S1 or go to S2 or go to S3, and these arrows are basically pointing in which direction the operations can go. So let's look at one simple example of, let's say, a garage door opener. So this is the table that is describing the garage door opener. And what are the possible states? For a door, usually that's the case, open or closed. So if we are down and we want to stay down, what will be our states? Basically, transition number is 0. We have no input because we want to stay down. We stay down, next state is down, and the output is none. Now, if we want to go from down to up, we need to activate the clicker, and that will be our transition 2, and the output is up motor. So how would you make that in a hardware? Oh, now it's working? Huh? Interesting. Well, this would be our hardware realization of the finite state machine that we described here. So what do we need? We definitely need some combinatorial logic that will open and close the door. And we need the clicker as a signal that tells us to open or close the door. And then here we need to return the next state to our flip-flop. Basically, that will determine is it up or down, and you have a clock to orchestrate the whole thing. Are you familiar with this? You should. You had that before. So what do we need when we're designing a processor? We will also use a finite state machine, but now our states are fetch, decode, and execute. What does it mean? Well, pretty much what I was showing you before. We had a PC that has to put the address in a memory, and that memory to write into instruction register. That would be our fetching state. We are loading the instruction into instruction register, so now we can perform that instruction. What is the instruction? Well, the code will tell us that. We have to read these bits and figure out what is our instruction, and then we need to execute it, which is the rest, like adding these two registers into third register. So what do you think, how many cycles do we need to do that? Let's say for fetch, how many cycles do we need? What do you mean 0? We need at least one cycle, but I would claim that we need a little bit more than that because we have a single bus. So the first step is that PC writes into address in a memory, and then the second step would be to write from a memory instruction into instruction register, and we'll see that we need a third step, which is, guess what? We have to move from instruction 1 to instruction B, which means we need to increase the PC. Program counter has to be increased. Theoretically, you can do that at the end when you finish the execution, but you will see that when you have, let's say, branching or any jumps, that PC may change in between, so you really want to have that increased at the fetch state. So let's see again, how do we represent these registers? Basically, we will use 16 of them in LC2200, and those 16 registers will have a 32 bits. So how many wires will be here, this D in? And how will be the out? Okay. And this write register is basically a signal that tells you when to write into register something. So if it's 0, that means we are not writing anything. If it's 1, we are writing something. How many wires is that? And this register number, or regno, I don't know how to read it, that's basically register number. So if we have a 16 registers, how many bits do we need to represent? So we need 4 of them. So that's description of that. We can perform these 3 operations in our AUL unit. Basically, we have AND, we have not, we have addition, not AND, subtraction, and there is a fourth command that is pretty much register plus 1. And that's because we will use that a lot, so that's a fourth instruction. PC also has a 32 bits. Our bus has a 32 bits, and the memory is 32-bit word with how many elements in a memory? What is the size of the memory if we have 32-bit words? It says there. 2 to the 32. Okay, so let's see now how our data path looks like. So this would be the bus going around. Here we have a PC that can, you can load something in PC if LDPC is 1, or you can write something on a bus if drive PC is 1. This is AUL. As I said, we have addition, not, and A minus B and A plus 1. And this function will have 2 bits, 0, 0, 0, 1, 1, 0, or 1, 1 to distinguish these 4 operations. Then you have 16 registers. You have a memory and instruction register. So let's see if we want to perform, again, this addition. What do? We have a PC that needs to write something into memory. Well, we are adding something called memory address register. What do you think? Why? Well, basically, this PC will write its information in MAR. Why don't we just let it load into memory? Because whatever it comes in, it will leak out, and it won't really be available in the next cycle. So we basically store in memory address register whatever PC gives us as the address. Then the next step is to store in register A our information, and then to load in register B, which is RY and RZ, and then we add the numbers, and that completes pretty much our data path. The last thing that we missed, and we'll see later why do we need this, we have a 1-bit register Z, that basically if you have any question like is A equal to B, if it's true, then Z will be 1. If it's false, it will be 0, and that will help us jump or branch and so on. So that's the data path. Now, what do we need to make it work? Yes. Exactly. We need a director to orchestrate our nice control unit. So to control that, you saw here that we have a bunch of control signals like load PC, load A, load B, or drive PC, drive AUL, and so on. So our drive signals are these. And then a load signals you have here, write memory signal, write register signal, AUL function, and register selector, which is basically register number. And we'll talk a little bit more about these functions when we get to examples. So if we take all these signals and put them in a table, basically sort them by drive signal, load signals, write signals, and so on, that would give you a current state of a processor. So how do we move from one state to another? So in one state, we wanted to write PC into a memory address register. So that means that this drive PC will be 1, and load MAR will be 1, and everything else will be 0. So that's how your table will look like. It would have here 1, and the load MAR 1, and everything else 0. Now to move to a next state, we basically need another element in our table that basically determines what will be the next state. So how do we do that? Well, we need some place where we're going to store these tables that I just showed you, basically the current state and the next state. So we have a state register that is telling the ROM where, and ROM means read-only memory. Why it's read-only? Can it be read-write? Well, think about it. This is your director. Can you overwrite your director? You have to listen what they tell you. So this is your director, and you can read its instructions, but you cannot really write into it. So basically, this state register will just tell you which address to read and whatever is in that address. On that address will be these bits here. 5 of them are drive, 8 of them are load and write, 2 of them are function bits, basically 4 operations that we need to code, and the number of registers. And then you will have a 5 bits that determine the next state. And we will get back to this picture in more details because we'll actually change this input. It won't be only 5 bits, but 10, but we'll get to that. So these are the macro states, as I said, fetch, decode, and execute. Now let's zoom in into fetch and what exactly we need to do. As I said, there are 3 steps. So the first step will be obviously to load PC into a memory address register. The second step will be to read what is on that address in a memory and store it into instruction register. And the fourth one will be to increase PC. Now, if you go back and look at here, I said that we are going to write PC into register A and also into a memory address register. Why am I doing that? Exactly, because otherwise I would need 4 steps. If I don't do this way, if I go here and write PC into MAR, and then address whatever is in a memory and that address store into instruction register, then here I would have to store PC first into A, then increment A plus 1 and store it into PC. Basically, just those are the steps for addition. So let's look how do we do this first step. Our drive PC will become 1, and the information from PC, which are 32 bits, will travel all the way back. And then register A and register MAR will allowed to write, which means load MAR and load A will be 1. Do you have any questions? So in our table that I show you, you will have again a bunch of zeros, but these red letters will have a value 1. You can ask. Now, clock cycle depends how do you determine the width of how long one cycle lasts. So you can do a couple of these in one cycle if your cycle is long enough. If it's shorter, then you may do only 1 or maybe 2. So it's a matter of design. But these are the steps. So I fetch 1 would be this one. And the reason why do you need 3 steps is because, again, you can write only one unit at a time on the bus. If you would have 2 buses, then maybe you could do this step together with the first one. But you have only 1 bus, so only one is writing, more of them can read. That's the whole concept. Okay, so now that we have the address in a memory, we access that, read it. So to let it out on the bus, we need to set drive memory to 1. And now we have, again, 32 bits traveling around, and instruction register reads them. So in this step, basically, this instruction written as a zeros and ones is loaded in instruction register. Okay? And then when we want to add A plus 1 to PC, because we loaded before PC into A, now I can just set this function to 1, 1. So if I set this one to 1, 1, it would increment A plus 1. Now I can write that result on my bus, and the PC will load it. Any questions? Is everything clear or nothing is clear? Because there are no reactions. Okay, good. So let's move on. So now if we look at our table of states, basically if our state is I fetch 1, which means state number is, let's say, these 4 zeros, we set it PC load to 1, PC drive to 1, and we read A and mar, so they are 1. Our functions are XX, which means we didn't use that operand, so we don't care what is it, and the same thing with the registers. And the next state is 0001. Now, how do you determine these states? Well, basically, you just pre-code them. Okay, we started from fetch. I fetch 1 will be all zeros. I fetch 2. This is the code for this instruction. This is the code for this instruction. So that's how you will be moving into next state. Once when you know that you're done with I fetch 1, then obviously next step is I fetch 2. So that's how you would do that. If you have a I fetch 2, if you're in that state, then our drive, basically memory, will write on a bus, and the instruction register will read it, and we will move to next one. And ifetch3 will again have AUL write on a bus, PC would read it, and we will have a function now to be 1, 1 because we use the addition A plus 1. The register number we didn't use, and here it says to be determined because basically we wrote the macro states. Macro states are fetch, decode, and execute. But now the question is, when I'm done with all fetching, where do I go next? That's why I left this one undetermined. So obviously the next step is to decode. How do we do that? Yes? Well, basically, we will read from our instruction register, where now the whole thing is loaded, we will read the opcode, which are first 4 bits. And we will determine, is it R-type, I-type, J-type, or O-type. Now, you're familiar with this, right? Okay? So once when we do that, basically our state, finite state machine looks more like this. I had fetch, and now I have to go to decode state to figure out which of the types do I have. And once when I have it, I have to go back to fetch. And we will discuss about decoding in a moment. We want to go to execute to see what happens then. Because for let's say if you have a branching or jumping, things may become more complicated, so this coding may also become slightly more complicated, but we'll get to that. Now execute. Now that I know that I want to, let's say, add 2 registers, I have to execute it. I don't know if you have noticed, but there was no data pad from instruction register to register file. So if we look at here, we left this open and nothing is attached to this register number. What do you think? Why? Because here we have the output of particular parts of instruction registers. So if I want to read Rx, I will read these bits. If I want to read Ry, and so on. And here is the op for instruction register. But the question is, how do we connect our control unit with the data pad? So what do we need to do? I should have bring you chocolates or something, coffee, to wake you up. I have a feeling that everyone is asleep. So, well, what do we do? Why do we need a multiplexer? Because we have 3 registers, let's say, in this operation, and we don't want to read all of them all the time. Basically, I need only one of them. And the easiest way to determine which 4 bits to read is to add a multiplexer, where register X will be 0, 0, register Y will be 0, 1, register Z is 1, 0. And then from the control unit, I will have to pass 2 bits to determine which of these numbers will actually be my register number. So if we go back to our read-only memory and control unit, this is how it would be attached. If you remember, we had a state register that was passing the 5 bits of address to ROM. It would read, and whatever is on that address will be on our outputs for drive bits, for load and write bits, for function. And now, before we had the 4 bits here called register number. Now we have actually only 2 bits, which are register selector, to determine which of these registers is going to be written into register file. Does it make sense? Why? Why it makes sense? Mm-hmm.
So there's no need to repeat those bits to the right number from the RAM or from the ROM A. So it's a lot more logical to just use the 2 bits coming out of the multiplexer to choose which bits from the original instruction
If you look at from the bus perspective, basically, if I have to read only 4 bits from instruction register, and I don't have a way of passing only 4 of them, I would have to kind of load here all 32, and then I would need some logic to determine which 4 do I need, which is pretty much exactly what we did with this multiplex. Okay, so now that we have that, this is how it's added on our data path. This register number is connected here. It was just too messy to draw the line. And this guy is coming from our, you can look at it as just another control signal, like drive memory. This would be another control signal coming from control unit. And here you would read RX, RY, or RZ pretty much from here. Okay, so our now table has slightly changed. We still have a drive signals, load signals, write signal, next state signal. Now instead of register number that has 4 bits, we have a register selector that has 2 bits. So we kind of made our system a little bit more efficient. So now if we want to add 2 numbers into registers, what do we need to do? How many steps? Don't think about cycles. How many steps do we need? How many these ADD 1, 2, 3, 4 do we need? Okay, let me ask you this. How do you determine how many steps do we need? Yeah, exactly. How many times do you have to write on a bus? So how many times do you have to? 3, exactly. So the first step is obviously load the that is on bits 23 to 20, RY. We are loading that into register A. So how do we do that? Well, we let this one to write, and then we read only these 4 bits, and we set register selector to 0, 1. And that will activate our 4 bits here. And then when we do that, we write that on the bus, and it's loaded into A. Questions? So the steps are the following. You read the RY parts of instruction register, which are 23 to 20 bits. You set register selector to 0, 1, and that will activate your register file. So basically on that address, whatever is on that address will be written on the bus, which is drive register is set to 1, and it will be loaded into A. So here we are talking about the address, and then here we are reading actual content of ry, and we are storing that into A, and we will be using them for addition. So now we have to do the same thing with rz. We are reading the address of rz, which are the bytes 3 to 0. We set now this rec cell to 1, 0, because it will let you read rz. And now we know the address to find the address for rz, for content for rz, and we write that on the bus and store it into B. And now we need to add them. How do we add that? Well, basically addition is 0, 0, so this function will be 0, 0. It would add content of A and B. It would write that on the bus by setting drive AUL to 1. And then we have to set write register to 1 so that we can write that into now Rx. How do we do that? Well, you select here that you want to write into Rx by setting here a rec cell to 0, 0, and set then this address here and the write to 1, and that would be the place where the content of this addition will be placed. This is slightly more complicated, so if you have any questions, feel free to ask. Yes. It's a good question. You're asking, do we really need a drive signal here? Well, what will happen, let's say you loaded something to A, and you don't want to perform any operation because it's all connected with wires. Unless you have this gate to prevent going to bus, it would just leak on. But in order to perform any of these particular operations on A, then you have to activate the function to a certain number. Was that the question? Okay. Yeah, I was thinking the same thing. If I have this control here, why do I need the extra control down there? But the thing is, even if nothing here is activated, if I have anything loaded here, it will just leak down. Because at the end, they're all wires, and they're somehow connected. Okay, so now our finite state machine has changed. We had before this macro states, just fetch, decode, and execute. And now we know that fetch is actually fetch 1, fetch 2, fetch 3. And then it basically decodes and goes to addition 1, addition 2, addition 3. So now our execution is done, if that was our operation. Now we need to go back to fetch. So basically we need to fetch another instruction. So what if we have a different type of instruction? What is this? What's it called? Jump and lock. And it has now 2 registers, and it has this, of course, opcode to determine what is the function, and we are not using the lower bits. So how that is performed? How many steps do we need? Okay, who can tell me what is this function about?
So it stores the address of the next line in original address. So
Okay.
in RY mostly, which we use original address.
Mm-hmm.
So that would store PC plus 2 in the original address.
No, PC plus 1.
PC plus 1 is the original address. And then it would load the PC with RX.
Exactly. So it looks like only 2 writing on the path. The good thing is now why we can do PC plus 1 immediately. Yes. Exactly. Now you have to remember that, because if you're doing this manually, like you have a homework or something, if you perform the fetching and you already incremented PC and now you want to execute the instruction, remember that PC is already PC plus 1, so don't add it one more. It will become PC plus 2 and mess up everything. So PC plus 1 needs to be stored in RY. RY because that's the definition of our instruction. So how do we do that? Who can read? Everything that has to happen is already marked with red. Go ahead. Okay, so we first drive the PC, okay, and do what? Write into register, and we particularly want to write to RY, which means we have to select RY. So that would be 0, 1 here in Rexel. And these two, when they're activated, what happens then? Nothing, we're done. So the only writing is PC goes to the bus, and now we have to store it into one of the registers in a register file, and to determine on which address we need to activate the address of RY, because that's where we want to store it. Okay, so next step is now writing RX to PC. Who can help me with this one?
Turn off write enable to the register file. So it's going to read from the registers.
Mm-hmm.
Change reg select to 0, 0, so that's looking at register X.
Mm-hmm.
Drive the register onto the bus, and then that loads into PC.
Exactly. So one more time, we know what is in register RX. Now I just have to select that I want to read what is in RX. And those 4 bits, which are the address for RX, will be activated here. We'll let it write on the bus by setting the RX to 1. And then we load that to PC. It wasn't that bad, right? Yes. I keep this red because we are constantly actually using one of the lines activated, either RX, RY, RZ. But technically, all 32 bits will be available here, and then we are selecting here which ones we are going to read. Any questions? Okay. So now let's look at the instruction load word. It's I type of instruction, and we want to write into register RX content of a memory on the address RY plus signed address offset. How many steps do we need? Well, we need at least 3, but most probably 4. So let's see how it's done. First, we want to set RY into register A, and we want to set signed offset into register B so that we can add these two. So once when we do that, then we need to that result stored into MAR so that MAR can tell us which address do we need to read. And once when we read that address, we store that into Rx. So let's go step by step. How do we do this first step? It's very similar to the previous case where we, again, allow us to read the content of instruction register and select the 01 case where RY address is available and store that into register number and then read what is on that address and allow that result to be free on the bus. So we set the drive register to 1 and then the register A can load that result. So now if you would make a table of these, basically all these red signals would become 1, all others will be 0, and you basically get the current state. And what would be our next state? It would be load word 2. This is state load word 1, and each one of them would have a particular code. If you remember in our control unit, the register state had the 5 bits, putting them back into the ROM. So those 5 bits would determine all our possible states. So now the second step is sign offset to store into B. Well, this is the only difference from here where you are adding 2 registers. Now you want to read the sign offset, which if you look at the instruction code, it says it has bits from 0 to 19. So now you want to this lower 20 bits with sign extend, read from instruction register and let it read on a bus. So here we are not going to use register selector. We are going to read directly these last 20 bits by setting drive off to 1. That's the only difference when you are adding 2 registers and when you are adding sign offset with some other number. That's clear? Okay, great. So now we need to store A plus B into memory address register. So how do we do that? Well, first we need to add A plus B by setting function to 0, 0. That's the addition. And whatever is the content of that, you set drive AUL to 1 and you let it write into load MAR. And the last step is to actually read what is on that address and store it into Rx. So now I'm going to set drive memory to 1 so that I can read that content. And I'm going to write into my registers. So write register has to be 1. And to find the address where I'm going to write, I need to set register select to 0, 0 so that I can write on Rx, and that will give me my address, and this will give me permission to write. So once when I have that, I don't think this one is supposed to be red. That's an error. Basically, this one is black. We can write on the bus only once. So that's it. Basically, we wrote our content into Rx. Do we have any questions? Okay, so what if we want to do branching? Branch if equal. How many steps do we need? Let's say we want to do this. If Rx is equal to Ry, then increase PC, write into PC a result of PC plus 1 plus sign address offset. If it's not true, then do nothing. So what do you think? How many steps? That's true. So obviously our finite state machine will have a optional branching. And if, let's say if it's true, if we need to do this, then we need how many steps? 6. And if we don't want to do that, 3. Yeah. So why do we need? Well, we need definitely one step to read Rx, and we need one step to read Ry, and then we need a step to ask, is it equal? So the first step is we need to, by the way, how do we ask is something equal to something? We don't have that operation here. Exactly. That's how you ask is A equal to B by subtracting A and B, and that's why we have this nice option here of asking, is it 0? So how do we store Rx into A? Well, the similar steps as before. We set the register selector to 0, 0. Then we read the content of IR on addresses 27 to 24. And that's our address that we activate here. And we read what is there. We let it on the bus and load it into A. What do we do next? We take RY and store into B. So again, the same steps. The only difference is the register selector is now 0, 1. And that gives you the new address. And you write that on the bus and load it into B. So now we do the following. We subtract A minus B. And we do that by setting function to 1, 0. So A minus B is performed. And that result now has to be written into Z. And actually, there's an extra step there, because if you look at this, the output of this are 32 bits. And our Z has only 1 bit. So we have a step in between asking, are the all bits equal to 0? If it's true, then it's 1. If it's false, then it's 0. So that's why Z has only 1 bit. We don't have to carry all 32 for the result. We just care, is it true or false? So what do we do next? So our final state machine now has changed again. We had ifetch1, ifetch2, and so on. And then we executed the instruction of branch if equal 1, 2, 3. And now we are at the point that if Z is equal to 0, we have to fetch a new instruction. If Z is equal to 1, we need to proceed. So let's see what happens if that is true. What do we need to do? If you remember here, we need to store in a PC, PC plus 1 plus assigned address offset. So the first step is what? Drive the PC on the bus and store it into A or B, doesn't really matter. Then the next step is we need to get the signed offset. Signed offset is again last 20 bits from here. You just drive this line and you write it into B. When we do that, we add these two numbers by setting function to 0, 0 and drive AUL and then write that into PC. Do we need to do anything else? Why we didn't have to do PC plus 1 plus offset? We already have a PC plus 1. So that's pretty much steps of that. So do you have any questions? Yes. actually Z has to go into our ROM, into our control. And actually I was thinking of leaving that to Kishore to finish up, but I can explain since you asked. So now the first problem is that we have to change our state coding. We had the 5 bits for coding, but obviously when you have a branching, you want to somehow code that. So if I have a Z equal to 0 and my state was 0, 1, 0, 0, 0, I would place 0 in front of that, and that would be case of Z equal to 0. And if it's 1, I will place 1 between the same state, which will kind of help me code the case of branching. And then that information, in addition to actually coding, why do you have to do that? Because you pretty much have to clone this ifetch1 for the case when you're returning right away to a new instruction, or the case when you're executing everything and then returning to that instruction. So Z is helping you distinguish those two. And on top of that, you have to code each one of these instructions, basically. Because if you have a branching and within a branching you want to do addition and so on, you may want to add in front of those 5 states that we had for this state register, you may want to add basically code for these instructions, which are 4 bits. So if I take those 4 bits and I put Z as a bit, and then I use my 5 bits for just different states that I can be in, that will give you a final control unit. And here is the example what happens in this ROM. Before I was telling you we had the 5 bits from a state register that is telling you from which state you're going. Suddenly we have a 10 bits because we added extra 5 bits. 4 of them are operational code, basically the code for addition, multiplication, and so on. And we added 1 more bit for Z to tell us are we branching this way or that way. And then we actually added 2 more bits. And then there is a modifier, and we're not going to go into details of that. There is a whole circuit that controls that will give you output of 5 bits. So for example, if you didn't have any branching in your code, then basically these 2 bits will overwrite all these additional bits that we added, and they will be just plain zeros, and we'll have 5 zeros and 5 states from the state register, and that will be your address in ROM. But if you did have any branching, then all these extra bits will kick in and basically determine what will be the address. Now for the output, we still have a 5 bits for a drive, 8 bits for a load and write, 2 bits for a function, 2 bits for a register selector, and this extra 2 bits, as I said, that we added to basically overwrite any extra coding we did to help us determine branching. If we had no branching, we don't need it, so we just set them all to 0. So basically in our table, now you will still have all these bits and the additional M and T that will determine the whole thing. So, any questions? No questions. This is boring or interesting? Yes. Can you just? I'm not exactly sure what these 2 bits stand for. Basically, their function is to control this modifier to see if there was any branching, and if it wasn't, just to overwrite everything to zeros. But I don't know exactly what is M and T for. Talk to me. About? Yes. Yes, you can find me under Alenka. I'm sorry, I didn't introduce myself. I'm Alenka Zajic, whatever last name you pronounce, but it's Alenka. so you can find my slides there. But they're very similar to Kishore's. I maybe have a little bit more examples. I figured that that's easier for me to learn. So. Yes.
I noticed there are like 10 bits going into the ROM and 24 coming out.
Mm-hmm.
So the 10 bits kind of say what instruction I want to get out, and the 24 at the end actually gives the individual control thing I want to
You can think about this as a pointer to the stack. Like, okay, this is the address I want to read. So you have 10 bits for the address, and then the ROM has probably 32 bits available, but we are using only 24. Okay, so that's all I had. If you don't have any other questions.